Hello, class. Okay, this recitation is heavily based on the common gate amplifier recitation um, that shows the low frequency common gate amplifier's gain as well as the frequency response of the common gate. So please review that recitation first because that has a load resistor RL in it, and I'm going to refer back to that recitation quite a bit here as we compare that load resistance RL to an active load device. Now we'll call that transistor Q2, the PMOS device here. So in this recitation, I kind of want to go over with you what happens in the frequency response as well as the low frequency gain of this circuit when instead of an RL resistor, we have an active load Q2. So let's go over that. In order to do that, I'm going to jump straight to the high frequency small signal model, okay, with the assumption that you can analyze low frequency small signal gain. All right, so let's do that. We're going to start with the transistor VGS1, our capacitor CGS1, because we're doing frequency response. Our R sig is at the source, Vin at the source. We have a GM1 VGS1. From drain to source, we have our R01. We have our V out node at the drain, perhaps a load capacitor. So let me draw it in the schematic here, CL, and some load capacitance here, also CL to ground. Now, instead of a load resistor at the drain going to a VDD or a small signal AC ground, we're going to have a PMOS device. So that at the drain of the PMOS device, looking in is R02, and we have a GM2 VGS2, and now the source is ground, and we have, let me actually draw, we have a gate to drain capacitor, whoops, shorting that out, a gate to drain capacitor for transistor 1, and now we also have a gate to drain capacitor for transistor 2, the PMOS device, but the gate of the PMOS device is ground because it's a DC voltage. So CGD2 is actually a capacitance from the drain node and the output node to ground. The gate to source capacitor disappears in Q2 because the gate and the source are both ground, if you can see there. And VGS2 of transistor Q2 is 0 volts because again, the gate and the source are both AC ground. So GM2 VGS2 actually goes away. And we've done this in a low frequency small signal before. The gate of Q1 is ground, and that makes sense because it's a common gate amplifier. So now if you look at this circuit, compare to the resistive loaded high frequency small signal model, you will see there's just very few differences. One of the differences is that you have this CGD2 and it's at the output node. So what you will have is your C equivalent of pole 2 will now be CL plus CGD1. That was the original one we had a load resistor plus CGD2. So we add a little extra capacitance at the second pole. We also can say that R equivalent 2, which was our output equivalent resistance from the V out node. In the prior example where it was RL in parallel with roughly R01, now it'll be approximately R01 in parallel with R02. So the R02, the output resistance of, or the drain resistance, I could call it, of the PMOS device replaces RL. The way that you could do this is to reanalyze the entire circuit's output resistance, and you will find this R02. Or you could just look going up into from V out, you can see GM2 VGS2 is open circuit, CGD2 does not matter. It's an open circuit in small and low frequency when we're talking about resistance, so you just have an R02. So it's R02 in parallel with the resistance seen looking into the drain of the common gate device, which we found in the previous recitation. I will not do again. It was approximately R01 when our sig is small, That was the approximation. If you assume R01 goes to infinity, which we have done in a low frequency gain analysis, then this R01 would go to infinity, and R equivalent would become R02. So it depends on how many assumptions that you make. Okay. So again, the majority of the change will be in your second pole in frequency response, which will become 1 over the new CL plus CGD1 plus CGD2 and R01 approximately in parallel with R02 rather than RL. So that second pole moves. The first pole does not move because the first pole was dependent here on the input side, and looking at the input resistance, there was some, there was a no, looking back at the input resistance, you have 1 over GM1 approximately, right, in parallel with R sig, and then your equivalent capacitance was CGS1. So we don't change the pole due to the input side, omega P1, much when we change the active load. In terms of gain, low frequency, small signal gain, so that's when we don't include capacitors. Our original equation derived last recitation was GM1 RL over 1 plus GM1 R sig. So now that RL will be replaced with R02. So the gain here will be based off of the gain derived in the previous common gate recitation, will be approximately GM1 times, now instead of RL, it'll be R02 over 1 plus GM1 times R sig. And now when we did this derivation, I have to warn you, we made the assumption that R01 went to infinity. Why did we make that assumption? Again, we made that assumption just to simplify the small signal analysis with the assumption that R01 does not do much, does not change the overall gain equation by much. You could include R01 because in the frequency analysis, we did include R01. So you can also go back and include R01 in this gain derivation. It just becomes more complicated. There's more equations to solve to get the result. Okay, so I hope that helps you understand a little bit about how to replace the resistor with an active load and gives you some understanding of what happens in a common gate amplifier when you do this.